Hello, my gentle stargazers. Tonight, we're going to journey back through time, far beyond anything human eyes have ever witnessed, to the very first stars that ever existed. Close your eyes if you'd like, settle into comfort, and let's drift together into the ancient darkness where the universe's first lights were about to awaken. Imagine, if you will, a universe without a single star. No gentle twinkle in the night sky, no warm sunlight filtering through clouds, no distant galaxies spinning their ancient dances. This was our universe for hundreds of millions of years after the Big Bang, a vast expanse of darkness punctuated only by the fading afterglow of creation itself. The cosmic dark age, as astronomers call it, stretched from about 380,000 years after the Big Bang to somewhere around 100 million years later, though these numbers shift gently as our understanding deepens. In this primordial darkness, the universe was fundamentally different from what we know today. The temperature had fallen from the unimaginable heat of the Big Bang to something more like the coldest depths of interstellar space today, perhaps 20 to 30 Kelvin above absolute zero. Matter existed, certainly, but only in its simplest forms. Hydrogen atoms drifted through the void, making up about 75% of all normal matter. Helium comprised nearly all the remaining 25%, with just the tiniest traces of lithium and beryllium, elements formed in those first few minutes after the Big Bang when the entire universe was hot enough for nuclear fusion. This pristine mixture of elements tells us something profound about those early times. There was no carbon to form the backbone of life as we know it, no oxygen to create water, no silicon to build rocky planets, no iron to form the cores of worlds. Every element heavier than lithium that exists in our universe today, every atom in your body except for the hydrogen, was forged either in the hearts of stars or in their explosive deaths. But in this dark age, none of that had happened yet. The universe was chemically pristine, untouched by stellar alchemy. The darkness wasn't perfectly uniform, though. Throughout this vast expanse of hydrogen and helium, tiny variations in density existed, seeds planted during the universe's first fraction of a second. These fluctuations were incredibly subtle, regions where matter was perhaps 1 part in 100,000 denser than average. Yet these minute differences would prove to be everything. They were the blueprint for all structure we see in the universe today, from the smallest dwarf galaxies to the largest superclusters stretching across hundreds of millions of light years. As we drift through this ancient darkness, we can sense something else present, something we cannot see directly, but whose gravitational influence shapes everything around it. Dark matter, that mysterious substance that even today we struggle to understand, made up about 85% of all matter in the universe. Unlike the hydrogen and helium gas, dark matter doesn't interact with light at all. It neither emits nor absorbs radiation, making it perpetually invisible to any telescope. Yet its gravity was already at work, slowly gathering both itself and normal matter into increasingly dense clumps. The process was achingly slow by human standards. Generation after generation could have passed, entire civilizations could have risen and fallen in the time it took for these density fluctuations to grow by even a tiny fraction. But the universe had nothing but time, and gravity, though the weakest of nature's fundamental forces, is relentless and patient. Where matter was slightly denser, gravity was slightly stronger, pulling in more matter from the surroundings, which made gravity stronger still, which pulled in yet more matter, in a gentle runaway process that would eventually birth the first stars. Picture these dark matter halos growing in the void like invisible cocoons, their gravity creating wells in the fabric of space-time itself. Normal matter, the hydrogen and helium gas, felt this gravitational pull and began flowing toward these invisible centers of attraction. The gas moved slowly at first, barely faster than walking speed, but as it fell inward, it gained energy and speed. When gas particles collided, some of their energy of motion converted to heat, warming the infalling material slightly. This warming created a delicate balance. Hot gas naturally wants to expand, pushing outward against gravity's inward pull. For the gas to continue collapsing and eventually form stars, it needed to shed this heat somehow. In today's universe, heavy elements and molecules help gas clouds cool efficiently through radiation. But in this primeval darkness, with only hydrogen and helium available, cooling was much more difficult. The gas could only cool through specific atomic transitions that released energy as infrared light, carrying heat away into the darkness. The first molecular hydrogen began to form as hydrogen atoms collided and occasionally stuck together. This was a crucial development, as molecular hydrogen could radiate heat more efficiently than atomic hydrogen alone. These molecules acted like tiny cooling agents, allowing the gas clouds to shed their heat and continue their gravitational collapse. Without this molecular cooling, the first stars might never have formed at all, and our universe would have remained dark indefinitely. As millions of years passed in this patient cosmic dance, the densest regions within dark matter halos continued to accumulate gas. The temperature in these regions rose to hundreds of Kelvin, still cold by stellar standards, but warm enough for the physics of collapse to change dramatically. The gas began to fragment, breaking apart into smaller clumps within the larger cloud. Each fragment continued its own collapse, racing its neighbours to see which would first achieve the density and temperature necessary for nuclear fusion to begin. We're watching the universe prepare for a transformation as profound as any in its history. For more than 100 million years, darkness had reigned absolute. But deep within these collapsing gas clouds, conditions were approaching those needed for nuclear fusion. The universe was about to witness the birth of its very first stars, and nothing would ever be the same again. Let's linger a moment longer in this cosmic dark age, this epoch of shadows that stretched across the young universe, like an endless night. Understanding this time helps us appreciate just how revolutionary the appearance of the first stars would be. The Dark Age wasn't simply an absence of starlight. It was a fundamentally different cosmic environment, one that shaped the conditions under which those first stars would eventually emerge. The universe during this time was expanding and cooling, continuing the process that began with the Big Bang itself. When the universe was about 380,000 years old, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms, an event cosmologists call recombination. Before this moment, the universe had been opaque to light, filled with a hot plasma that scattered photons in all directions. After recombination, light could finally travel freely through space, and the universe became transparent. This ancient light, stretched by billions of years of cosmic expansion, reaches us today as the cosmic microwave background radiation, a faint whisper of heat coming from every direction in the sky. Following recombination, the universe entered what we might think of as its quiet age. The brilliant fireball of the Big Bang had faded, leaving behind a cooling cosmos filled with neutral gas and invisible dark matter. The temperature continued to drop as space expanded, falling from about 3,000 Kelvin at recombination to perhaps 20 Kelvin by the time the first stars were ready to form. This cooling universe was filled with gentle radiation. The afterglow of the Big Bang redshifted into infrared wavelengths invisible to human eyes. Sound waves rippled through this primordial gas, vast acoustic oscillations that had been frozen in place at recombination. These sound waves left their imprint on the distribution of matter, creating a subtle pattern of density variations that astronomers can still detect today in the clustering of galaxies. The wavelength of these ancient sound waves was enormous, about 490 million light-years in today's expanded universe, setting a fundamental scale for cosmic structure. During the Dark Age, the universe was also remarkably quiet in terms of energetic events. There were no supernovae to shock the gas, no stellar winds to stir it, no ultraviolet radiation to ionize it. The only significant source of energy was the gravitational potential energy released as matter fell into the growing dark matter halos. This energy heated the gas slightly, but without efficient cooling mechanisms, it often wasn't enough to trigger rapid collapse. The distribution of dark matter during this epoch followed patterns set by quantum fluctuations in the universe's earliest moments. These fluctuations, magnified by cosmic inflation and then grown by gravity, created a cosmic web of dark matter. The densest regions, where multiple filaments of the web intersected, would become the sites of the first star formation. Between these dense nodes stretched vast voids, regions of space that contained very little matter and would remain relatively empty even to this day. Within the growing dark matter halos, an interesting phenomenon was occurring. As normal matter fell inward, it didn't just heat up uniformly. The gas developed complex velocity patterns, swirling and churning as different streams of infalling material collided and merged. These motions created turbulence within the gas clouds, adding another layer of complexity to the collapse process. This turbulence could either help or hinder star formation, sometimes creating local density enhancements that accelerated collapse, other times stirring the gas so vigorously that it resisted gravitational compression. The chemical simplicity of the Dark Age universe had profound implications for how gas behaved. Without heavy elements or complex molecules, the gas had very limited ways to cool itself. Atomic hydrogen could only radiate efficiently at very specific temperatures, creating bottlenecks in the cooling process. When gas reached about 8,000 Kelvin, hydrogen atoms could be excited to higher energy levels and then radiate that energy away. But between different temperature ranges, cooling was much less efficient, causing the gas to pile up at certain temperatures, like traffic at a bottleneck. The formation of molecular hydrogen was therefore crucial, but it too faced challenges in this primeval environment. Molecular hydrogen forms most efficiently on the surfaces of dust grains in today's universe, but no dust existed in the Dark Age. Instead, H2 molecules had to form through a more complex process, involving free electrons or hydrogen atoms in excited states as catalysts. This process was slow and inefficient, but given enough time and the right conditions, enough molecular hydrogen accumulated to enable further cooling. As the Dark Age progressed, the universe was slowly building up the conditions necessary for star formation. Dark matter halos grew through mergers and accretion, eventually reaching masses of about 1 million times the mass of our Sun. Within these halos, gas accumulated in the central regions, slowly cooling and condensing. The density contrast between the densest regions and the average universe grew from 1 part in 100,000 to 1 part in 1,000, then 1 part in 100, growing ever stronger as gravity's patient work continued. The magnetic fields in the Dark Age universe were extremely weak, perhaps 1/1000th or less of the strength of Earth's magnetic field today. These primordial magnetic fields, whose ultimate origin remains somewhat mysterious, were amplified by the turbulent motions of the gas, but remained too weak to significantly affect the collapse process. This is quite different from star formation today, where magnetic fields can provide crucial support against gravity and channel gas flows along field lines. Temperature fluctuations in the cosmic microwave background radiation created subtle effects on the gas temperature throughout the universe. Regions where the background radiation was slightly warmer heated the gas a tiny bit more, while cooler regions allowed for slightly more efficient cooling. These variations were minuscule, but in a universe balanced on the edge of star formation, even tiny differences could determine where the first stars would appear. The Dark Age universe was also remarkably uniform in its properties across vast distances. Unlike today's universe, with its rich variety of environments from galaxy clusters to voids, the Dark Age cosmos looked much the same everywhere on large scales. This uniformity meant that when conditions finally became right for star formation, it likely began nearly simultaneously in many places across the observable universe, like flowers blooming across a meadow when spring conditions finally arrive. As we near the end of the Dark Age, somewhere around 100 million years after the Big Bang, the stage was finally set. In the densest regions of the most massive dark matter halos, gas had accumulated to densities millions of times greater than the cosmic average. The temperature in these regions had risen to several hundred Kelvin, and molecular hydrogen had formed in sufficient quantities to enable efficient cooling. The universe stood on the threshold of a new era, ready to light its first stellar fires and banish the darkness forever. The anticipation builds as we imagine these moments before the first star. Throughout the universe, thousands or perhaps millions of gas clouds teetered on the edge of collapse, each racing toward the critical conditions needed for fusion. The universe held its breath, so to speak, waiting for that first nuclear flame to ignite. And when it did, when that first star began to shine, it would mark the end of the cosmic dark age and the beginning of the universe as we know it, filled with light and heat and the promise of chemical complexity to come. Now we must turn our attention to the subtle architecture of the early universe, those tiny imperfections in the cosmic fabric that would grow to become the scaffolding for the first stars. These primordial density fluctuations, born in the universe's first fraction of a second, carry within them the blueprint for every structure we see in the cosmos today. The story of these fluctuations begins during cosmic inflation, that brief but dramatic period of exponential expansion that occurred when the universe was less than a trillionth of a trillionth of a trillionth of a second old. During inflation, quantum mechanical uncertainties in the fabric of space-time itself were stretched to macroscopic scales. These quantum fluctuations, normally confined to subatomic dimensions, were inflated to sizes larger than the observable universe today. When inflation ended and the universe resumed its more sedate expansion, these fluctuations were frozen in place, creating regions where matter and energy were slightly more or less dense than average. The amplitude of these primordial fluctuations was remarkably small, typically just 1 part in 100,000. This means that if the average density of matter in a region was, say, 1 hydrogen atom per cubic meter, the densest regions might have had 1.1 atoms per cubic meter, while the least dense had 0.99999. Such tiny differences seem almost negligible, yet they contain the seeds of all future cosmic structure. Gravity, patient and persistent, would nurture these seeds over millions of years, growing them into the dark matter halos that would cradle the first stars. Dark matter played the leading role in this cosmic construction project. Because dark matter doesn't interact electromagnetically, it couldn't be pushed around by radiation pressure the way normal matter could. While normal matter remained coupled to the intense radiation field of the early universe, oscillating in acoustic waves like a cosmic symphony, dark matter simply fell inward wherever gravity was strongest. This gave dark matter a crucial head start in the structure formation process. By the time of recombination, when normal matter finally decoupled from radiation and could begin falling into gravitational wells, dark matter had already created a network of density enhancements throughout the universe. These dark matter perturbations had grown from 1 part in 100,000 to perhaps 1 part in 1,000, a 100-fold increase that gave normal matter ready-made gravitational wells to fall into. Without dark matter's head start, the first stars might not have formed until billions of years later, if at all. The growth of dark matter halos followed a hierarchical pattern, with smaller structures forming first and then merging to create larger ones. The first halos to collapse were relatively small, with masses of perhaps 10,000 to 100,000 times the mass of our Sun. These mini-halos were too small to form stars on their own, as their gravitational wells weren't deep enough to compress gas to the necessary densities. But through mergers and continued accretion, they grew into larger structures. When dark matter halos reached masses of about 1 million solar masses, something special happened. Their gravitational wells became deep enough that infalling gas could be heated to several thousand Kelvin, hot enough for hydrogen atoms to be excited and radiate energy efficiently. This cooling allowed the gas to compress further, setting the stage for the formation of the first stars. These million solar mass halos, roughly 1 billion times smaller than the dark matter halo of our Milky Way galaxy today, were the cradles of the first stellar generation. The internal structure of these early dark matter halos was relatively simple compared to galactic halos today. They had smooth density profiles, increasing gradually from the outskirts to a dense core. The density at the center could be millions of times higher than at the edge, creating a steep gravitational well that focused infalling gas toward a central concentration. Unlike modern galaxy halos, which have been stirred and disrupted by billions of years of mergers and interactions, these primordial halos were pristine and undisturbed. As normal matter fell into these dark matter halos, it underwent a complex process called virialization. The gas initially fell inward at speeds of several kilometers per second, gaining kinetic energy as it descended into the gravitational well. When gas streams from different directions collided near the center of the halo, their ordered infall motion was converted into random thermal motion, heating the gas. This process established a rough equilibrium, with the gas pressure balancing gravity at a temperature related to the depth of the gravitational well. The virial temperature, as astronomers call this equilibrium temperature, was typically a few hundred to a few thousand Kelvin for the first star-forming halos. This temperature was crucial because it determined whether the gas could cool efficiently. If the virial temperature was too low, below about 200 Kelvin, molecular hydrogen couldn't form efficiently, and the gas couldn't cool. If it was too high, above about 10,000 Kelvin, molecules would be destroyed by collisions, again preventing cooling. The sweet spot for first star formation was halos with virial temperatures between about 1,000 and 8,000 Kelvin. Within these Goldilocks halos, the gas didn't collapse uniformly. Instead, it developed a complex structure of filaments and sheets, following the cosmic web pattern of the dark matter. Gas flowed along filaments toward the nodes where they intersected, creating regions of enhanced density. These nodes, located near the centers of dark matter halos, became the sites where the first stars would form. The filamentary structure also created preferential directions for angular momentum, causing the gas to rotate as it collapsed. The role of angular momentum in these early collapses cannot be understated. As gas fell inward, even tiny initial rotations were amplified by conservation of angular momentum, like a figure skater spinning faster as she pulls in her arms. This rotation created centrifugal forces that resisted collapse perpendicular to the rotation axis, causing the gas to flatten into a disc-like structure. Within these discs, gas could only collapse further by either transporting angular momentum outward or fragmenting into multiple cores that could orbit each other. Turbulence within the collapsing gas added another layer of complexity. As different streams of infalling gas collided and merged, they created a cascade of swirling eddies at different scales. This turbulence could either promote or inhibit star formation. On one hand, turbulent compression could create local density enhancements that accelerated collapse. On the other hand, turbulent pressure could provide support against gravity, slowing or even preventing collapse in some regions. The balance between these effects helped determine where within a halo stars would actually form. The chemical processes occurring within these collapsing clouds were surprisingly complex despite the simple composition of primordial gas. As hydrogen atoms collided at temperatures above a few hundred Kelvin, some formed H2 molecules through a series of reactions. First, a hydrogen atom and an electron would combine to form an H- ion, which could then react with another hydrogen atom to form H2 plus an electron. Alternatively, two hydrogen atoms could combine in the presence of a third hydrogen atom, which carried away the excess energy. These reactions were slow and inefficient, but given the enormous timescales available, enough molecular hydrogen formed to enable cooling. Once formed, molecular hydrogen could cool the gas through rotational and vibrational transitions. When H2 molecules collided with hydrogen atoms, they could be excited to higher rotational or vibrational states. They would then radiate this energy away as infrared photons, removing heat from the gas. This cooling was most efficient at temperatures between about 200 and 2000 Kelvin, creating a characteristic temperature range for the first star-forming clouds. The density structure within collapsing gas clouds showed remarkable patterns. As gas cooled and condensed, it didn't maintain a uniform density, but instead developed a centrally concentrated profile. The density might increase by factors of millions or billions from the edge of the cloud to its center. This central concentration was crucial for star formation, as only in the very densest regions could hydrogen fusion eventually begin. The density profile typically followed a power law, with density proportional to radius raised to some negative power, creating a steep gradient that funneled gas toward the center. Magnetic fields, though weak in the early universe, still played a subtle role in shaping the collapse. As gas compressed, any existing magnetic fields were amplified, potentially becoming strong enough to affect gas dynamics in the densest regions. These fields could channel gas flows along field lines and transport angular momentum through magnetic braking, where field lines threading through the rotating gas acted like elastic bands, transferring rotation energy outward. However, the weakness of primordial magnetic fields meant their effects were generally secondary to gravity and gas pressure. The interplay between different physical processes created a rich variety of possible outcomes. In some halos, a single massive gas clump might collapse monolithically to form one enormous star. In others, the gas might fragment into multiple clumps, each forming its own star. The details depended sensitively on the initial conditions, the mass and spin of the dark matter halo, the temperature and density of the infalling gas, the efficiency of cooling, and the level of turbulence. Small differences in these parameters could lead to dramatically different results. As we observe these seeds of first light preparing to bloom, we can appreciate the delicate balance of forces at work. Gravity pulls inward, pressure pushes outward, rotation provides centrifugal support, cooling removes thermal energy, and turbulence stirs the pot. The first stars would emerge from this complex interplay, their properties determined by the precise balance achieved in each collapsing cloud. The universe had spent over 100 million years setting the stage, and now, finally, the first acts of stellar drama were about to begin. The actual formation of the first stars was a process both violent and graceful, a cosmic ballet of collapsing gas and growing protostars that would fundamentally change the universe. Let's follow this process in detail, watching as pristine primordial gas transforms into the universe's first nuclear furnaces. Deep within a dark matter halo, conditions have finally become right for star formation. The gas has cooled to a few hundred Kelvin through molecular hydrogen radiation, and gravity has compressed it to densities perhaps 1 million times greater than the average density of matter in the universe. But this is still far from stellar densities. The gas must compress by another factor of 1 trillion or more before nuclear fusion can begin. This enormous compression happens through a series of distinct phases, each with its own physical characteristics and challenges. The initial collapse phase begins when a region of gas becomes gravitationally unstable. This occurs when the gravitational energy exceeds the thermal and turbulent energy supporting the cloud. The characteristic mass for this instability, called the Jeans mass, depends on the temperature and density of the gas. For the conditions in primordial halos, the Jeans mass was typically between 100 and 1,000 solar masses, much larger than most stars forming today. This large Jeans mass is one reason why the first stars were probably much more massive than typical modern stars. As the cloud begins its collapse, it doesn't fall inward uniformly. Instead, the collapse proceeds in an inside-out fashion, with the central regions collapsing faster than the outer regions. This creates a density profile that steepens over time, with the central density increasing much more rapidly than the density at the cloud's edge. The collapse velocity increases inward as well, reaching several kilometers per second in the central regions while remaining subsonic in the outer envelope. During these early stages, the collapse is nearly isothermal, meaning the temperature remains roughly constant despite the compression. This is possible because molecular hydrogen cooling is very efficient at these densities and temperatures, radiating away the heat generated by compression almost as fast as it's produced. The infrared photons emitted by the cooling molecules escape freely from the cloud, carrying energy away into space. This efficient cooling allows the collapse to proceed rapidly, on a timescale of perhaps 10,000 to 100,000 years. But as the density continues to increase, something important changes. When the central density reaches about 100 billion particles per cubic centimetre, still only about 1/10,000th the density of water, the cloud becomes opaque to its own cooling radiation. The infrared photons emitted by molecular hydrogen can no longer escape freely, but are absorbed and re-emitted multiple times before leaving the cloud. This transition from optically thin to optically thick marks a crucial turning point in the collapse. Once the central region becomes opaque, it can no longer cool efficiently. The heat generated by compression becomes trapped, causing the temperature to rise. This creates a pressure-supported core at the center of the collapsing cloud, a protostellar core that will eventually become the star itself. This core is initially only about the size of our solar system today and contains just a small fraction of a solar mass, but it will grow rapidly through accretion. The formation of this first hydrostatic core, as astronomers call it, doesn't stop the overall collapse. Gas from the surrounding envelope continues to rain down onto the core's surface at supersonic speeds, creating an accretion shock where the infalling gas slams into the core. At this shock front, the ordered infall motion is converted into random thermal motion, heating the gas to thousands of Kelvin. This hot, shocked gas then settles onto the core, adding to its mass and causing it to contract and heat up further. The accretion rate during this phase is prodigious by modern star formation standards. Matter falls onto the protostar at rates of perhaps 1/100th to 1/10th of a solar mass per year. For comparison, stars forming in our galaxy today typically accrete at rates 1,000 to 1,000,000 times slower. This rapid accretion is possible because the primordial gas lacks the heavy elements and dust that create radiation pressure and stellar winds in modern star formation. Without these feedback mechanisms to slow or halt accretion, the first stars could grow very rapidly. As the protostellar core grows, its internal temperature and pressure increase. When the central temperature reaches about 2000 Kelvin, molecular hydrogen begins to dissociate back into atomic hydrogen. This dissociation absorbs enormous amounts of energy, temporarily halting the temperature rise and causing the core to collapse further. This creates a second collapse phase, even more dramatic than the first, as the core shrinks from solar system size to something more like the size of Jupiter's orbit. The second collapse ends when all the molecular hydrogen in the core has dissociated. Without this energy sink, the temperature begins rising rapidly again, creating a second hydrostatic core. This core is much smaller and denser than the first, with a radius of perhaps a few solar radii and a mass of a few hundredths of a solar mass. The central temperature is now around 10,000 Kelvin, hot enough to ionize hydrogen atoms. The protostar has become a hot, glowing ball of ionized gas, though still far from hot enough for nuclear fusion. The structure of the accreting protostar is complex and dynamic. The core is surrounded by a thick envelope of infalling gas which forms an accretion disk if the cloud had significant rotation. This disk spreads outward as angular momentum is transported by turbulence, magnetic fields, or gravitational instabilities. Matter spirals inward through the disk, slowly losing angular momentum until it can fall onto the protostar. The disk also provides a channel for outflows, as some of the accretion energy can drive bipolar jets perpendicular to the disk plane. As accretion continues, the protostar faces a critical challenge. The energy released by accretion, equal to the gravitational potential energy of the infalling matter, must be radiated away for accretion to continue. This luminosity can become enormous, potentially exceeding 1,000,000 times the luminosity of our Sun even before fusion begins. For modern star formation, this accretion luminosity creates radiation pressure that can halt or reverse the infall. But for the first stars, forming from metal-free gas, the situation was different. Without heavy elements, the opacity of primordial gas was much lower than modern star-forming gas. This means radiation could escape more easily, reducing the radiation pressure on infilling matter. Additionally, the lack of dust grains meant there was less coupling between radiation and matter. These factors allowed accretion to continue to much higher masses than would be possible today, potentially creating stars of 100, 500, or even 1,000 solar masses. The protostar's internal structure evolves as it grows. Initially, energy transport is dominated by convection, with hot bubbles of gas rising and cool gas sinking in a constant churning motion. But as the protostar contracts and heats up, radiation becomes increasingly important for energy transport. The transition from convective to radiative energy transport occurs first in the core and gradually spreads outward as the star evolves. When the central temperature reaches about 1,000,000 Kelvin, an important nuclear reaction begins, though it's not yet hydrogen fusion. Deuterium, the heavy isotope of hydrogen present in trace amounts from the Big Bang, begins to fuse with normal hydrogen to form helium-3. This deuterium burning provides a small but significant energy source that temporarily halts the contraction of the protostar. For a brief period, perhaps a few thousand years, the protostar maintains a quasi-stable state, supported by deuterium fusion, while continuing to accrete matter. But deuterium is quickly exhausted, as it makes up only about 2 parts in 100,000 of the primordial gas. Once deuterium burning ends, contraction resumes, and the central temperature continues to rise. The protostar is now racing toward the conditions needed for sustained hydrogen fusion. The central temperature climbs past 5 million Kelvin, then 10 million, approaching the critical threshold where hydrogen nuclei can overcome their electrical repulsion and fuse together. The path to hydrogen ignition isn't smooth. As the temperature rises, different regions of the star reach fusion conditions at slightly different times. The first fusion reactions might occur in hotspots created by convective fluctuations or compression waves. These initial fusion events are sporadic and localized, not yet providing steady energy generation. But as the central temperature continues to rise and more of the core reaches fusion conditions, the energy generation becomes more stable and centrally concentrated. The moment of hydrogen ignition marks the true birth of the star. When the central temperature exceeds about 15 million Kelvin, the rate of hydrogen fusion becomes sufficient to balance the energy radiated from the star's surface. The contraction that has driven the star's evolution finally stops, replaced by a new equilibrium between gravity pulling inward and fusion energy pushing outward. The protostar has become a true star, a stable nuclear furnace that will shine for millions of years. But even after hydrogen ignition, the star's formation isn't complete. Accretion continues from the surrounding envelope and disk, adding mass to the young star. This continued accretion presents new challenges, as the star must adjust its structure to accommodate the added mass, while maintaining nuclear burning in its core. The star's radius and luminosity fluctuate as it finds a new equilibrium after each major accretion event. The final mass of a population 3 star was determined by when accretion finally stopped. Several mechanisms could halt accretion. If the star became massive enough, its radiation pressure might finally overcome gravity and blow away the remaining gas. Alternatively, if multiple stars formed in the same cloud, their combined feedback could disrupt the accretion flow, or the gas supply might simply be exhausted, with all available material either accreted onto stars or expelled from the halo. Current theories suggest the first stars typically reached final masses between 10 and several hundred solar masses, with some possibly exceeding 1,000 solar masses. These masses are far larger than all but the most exceptional stars forming today. The exact mass distribution of population Thral stars remains uncertain and is one of the most important questions in early universe astronomy. What we do know is that these massive stars, born from the collapse of pristine primordial gas, were unlike anything in the modern universe. The birth process we've followed, from the first gravitational instability to the ignition of hydrogen fusion, took perhaps a few 100,000 years in total. This might seem long by human standards, but it's remarkably fast compared to the 100 million years the universe waited for conditions to become right for star formation. And once born, these massive stars would live fast and die young, burning through their nuclear fuel in just a few million years before ending their lives in spectacular explosions that would seed space with the first heavy elements. Now that we've witnessed their birth, let's explore what these first stars were actually like. Population 3 stars, as astronomers call them, were remarkable objects, fundamentally different from the stars we see in tonight's sky. Their unique characteristics stem directly from their primordial composition and the special conditions under which they formed. The most striking feature of population 3 stars was their enormous mass. While our Sun is a relatively typical star by modern standards, and most stars forming today are actually smaller than the Sun, the first stars were giants among giants. Theoretical models suggest they ranged from perhaps 10 solar masses at the small end to several hundred or even 1,000 solar masses at the upper extreme. The typical population 3 star was probably between 40 and 120 solar masses, making it larger than all but the most exceptional stars in the modern universe. This tendency toward high masses arose from the physics of primordial gas. Without heavy elements to provide efficient cooling, the gas clouds from which these stars formed remained relatively warm during collapse. This warmth meant that larger amounts of gas were needed to overcome thermal pressure and initiate gravitational collapse. The gene's mass, that critical mass above which gravity wins over pressure, was much larger in primordial conditions than in the metal-enriched gas clouds where stars form today. The surface temperatures of population 3 stars were extraordinary, A massive population star of 100 solar masses would have had a surface temperature of perhaps 100,000 Kelvin or more, compared to our Sun's relatively cool 5,800 Kelvin. This extreme temperature meant these stars emitted most of their light in the far ultraviolet range, with photons energetic enough to ionize hydrogen atoms many light years away. The visible light from such a star would have appeared blue-white, though with an intensity that would have been blinding to human eyes even from enormous distances. The luminosity of these stellar giants defied comprehension. 100 solar mass population 3D star would shine with the power of several million suns. The most massive examples, those approaching 1,000 solar masses, could have luminosities exceeding 10 million times our Sun's output. This prodigious energy output came from the enormous rate of nuclear fusion in their cores, where temperatures exceeded 50 million Kelvin and densities reached hundreds of grams per cubic centimetre. Every second, these stars converted millions of tons of hydrogen into helium, releasing energy equivalent to billions of nuclear weapons. The internal structure of population 3 stars differed significantly from modern stars of similar mass. Without heavy elements, their opacity was much lower, meaning radiation could travel more easily through their interiors. This affected how energy moved from the fusion-powered core to the surface. In the cores, where temperatures were highest, energy transport was dominated by radiation. Photons carried energy outward, bouncing countless times off particles but gradually diffusing toward the surface. Further out, where temperatures dropped below about 10 million Kelvin, convection took over, with massive cells of hot gas rising and cooler gas sinking in a constant circulation pattern. The size of these stars was remarkable. Despite their enormous mass, population 3 stars weren't proportionally larger than modern stars. 100 solar mass population 3 star might have had a radius of only 5 to 10 times our Sun's radius. This compact size, combined with their huge mass, created surface gravities hundreds of times stronger than Earth's. The escape velocity from their surfaces approached a significant fraction of the speed of light, requiring enormous energies to lift material away from the star. The nuclear fusion processes in population 3 stars follow different patterns than in metal-enriched stars. In stars like our Sun, the carbon-nitrogen-oxygen cycle provides an efficient pathway for hydrogen fusion at relatively low temperatures. But population 3 stars initially had no carbon, nitrogen, or oxygen. They relied entirely on the proton-proton chain, the same basic fusion process that powers our Sun, but operating at much higher temperatures and rates. Only later in their evolution, after creating carbon in their cores, could they utilize the more efficient CNO cycle. The lack of metals also affected the star's stability. In modern massive stars, metal-driven opacity creates radiation pressure that can drive powerful stellar winds, removing significant mass over the star's lifetime. Population 3 stars, with their lower opacity, had much weaker winds, at least initially. This meant they retained most of their birth mass throughout their lives, maintaining their extreme properties until their final explosive deaths. Some models suggest the most massive population 3 stars might have experienced episodic mass loss through pulsational instabilities, but this remains debated among theorists. The rotation of population 3 stars added another dimension to their complexity. As gas collapsed to form these stars, any initial rotation was amplified by conservation of angular momentum. Some population 3 stars might have been rotating at significant fractions of their breakup speed, where centrifugal force at the equator would equal gravity. Such rapid rotation would have deformed the stars into oblate spheroids, wider at the equator than at the poles. This rotation would also have created circulation patterns that mixed material between different layers, affecting the star's evolution and eventual fate. The magnetic fields of population 3 stars remain poorly understood. While the primordial universe had only weak seed magnetic fields, the turbulent formation process and possible differential rotation within these stars could have amplified these fields dramatically. Some researchers suggest population 3 stars might have developed magnetic fields millions of times stronger than our Sun's. These fields could have created star spots, channeled stellar winds along field lines, and contributed to angular momentum transport within the star. The chemical evolution within population 3 stars was a one-way journey from simplicity to complexity. Starting with pure hydrogen and helium, these stars gradually built heavier elements through nuclear fusion. When core hydrogen was exhausted, helium fusion began, creating carbon and oxygen. In the most massive examples, fusion continued through successively heavier elements: neon, magnesium, silicon, and eventually iron. Each new fusion phase occurred at higher temperatures and proceeded more rapidly than the last, accelerating the star toward its ultimate fate. The surface composition of population 3 stars would have remained pristine throughout most of their lives. Unlike modern stars, which are born with heavy elements that can be detected in their spectra, population 3 stars would have shown only hydrogen and helium absorption lines. Only in their final stages, if convection or rotation brought processed material to the surface, might heavier elements have appeared in their spectra. This chemical purity would make population 3 stars instantly recognizable if we could observe them directly, though none have yet been definitively detected. The environments around population 3 stars were harsh beyond imagination. Their intense ultraviolet radiation created enormous ionized regions, called HI regions, extending for tens or even hundreds of light years. Within these bubbles, hydrogen was kept almost completely ionized, glowing with a characteristic red light as electrons recombined with protons, only to be ionized again. The radiation pressure from these stars could accelerate nearby gas to hundreds of kilometers per second, creating expanding shells and possibly triggering or suppressing star formation in neighboring regions. The heating effect of population 3 stars extended even further than their ionizing radiation. Their photons, even those not energetic enough to ionize hydrogen, heated the surrounding gas through various absorption processes. This heating could raise the temperature of gas hundreds of light years away to thousands of Kelvin, fundamentally altering the conditions for any subsequent star formation. This thermal feedback was one of the ways population 3 stars influenced their cosmic neighborhoods. Some population 3 stars might have had companions, forming as binary or multiple star systems. The dynamics of such systems would have been spectacular, with stars massive enough to significantly distort each other's shapes through tidal forces. Mass transfer between companions could have occurred, potentially creating even more massive stars, or altering evolutionary pathways. When one star in such a system exploded as a supernova, it might have disrupted the system entirely or left behind exotic remnants like binary black holes. The variability of population 3 stars is another fascinating aspect. Some might have been variable stars, changing in brightness over time due to pulsations, eruptions, or other instabilities. The most massive examples might have experienced the pair instability, where gamma rays in the core became energetic enough to create electron-positron pairs, temporarily reducing pressure and causing the star to contract and heat up violently. These pulsations could have ejected significant mass before the star's final explosion. The question of how long population 3 stars lived is crucial for understanding their impact on the early universe. 100 solar mass population 3 star would exhaust its core hydrogen in about 2 to 3 million years, incredibly brief compared to our Sun's 10 billion year hydrogen-burning lifetime. The most massive examples, those approaching 1,000 solar masses, might have lived for only a few 100,000 years. These short lifetimes meant that population 3 stars appeared and disappeared like cosmic fireflies, briefly illuminating the darkness before vanishing in spectacular explosions. The energy balance of population 3 stars was precarious. Their enormous luminosities meant they were constantly on the edge of stability, with radiation pressure nearly balancing gravity. Small perturbations could trigger dramatic responses, from gentle oscillations to violent eruptions. This instability increased as the stars evolved and their cores produced heavier elements, changing the opacity and energy generation rate. The final stages of their lives were likely marked by increasing variability and mass loss. Understanding population the 3 stars requires us to push our theoretical models to extremes. The physical conditions in their cores, with temperatures exceeding 100 million Kelvin and densities approaching nuclear values, challenge our understanding of matter and radiation. Quantum effects become important, relativistic corrections are necessary, and the equation of state of matter becomes exotic. Computer simulations of these stars require sophisticated physics and enormous computational resources. Despite their extreme nature, or perhaps because of it, population 3 stars played a gentle but crucial role in the universe's evolution. They were the alchemists that transformed primordial hydrogen and helium into the first heavy elements. They were the lights that began the process of Royonizing the universe, clearing away the cosmic fog. And they were the progenitors of the first black holes, some of which might have grown into the supermassive monsters we see at the centres of galaxies today. These remarkable stars, though long vanished, left an indelible mark on cosmic history. Deep within the cores of population 3 stars, nature's most fundamental process was at work, transforming matter into energy through nuclear fusion. Let's journey into these stellar hearts and explore the remarkable nuclear processes that powered the first stars and began the universe's chemical enrichment. The story begins with hydrogen fusion, the primary energy source for all stars. In population 3 stars, this process started when core temperatures exceeded about 15 million Kelvin. At these temperatures, hydrogen nuclei simple protons moved fast enough to occasionally overcome their mutual electrical repulsion and come close enough for the strong nuclear force to bind them together. This fusion didn't happen directly. 4 hydrogen nuclei don't simply collide simultaneously to form helium. Instead, the process occurred through a series of steps known as the proton-proton chain. The first step of this chain was the slowest and most difficult. 2 protons had to collide, and during that brief encounter, one had to transform into a neutron through beta plus decay, emitting a positron and a neutrino. This process, requiring the weak nuclear force, happened incredibly rarely. On average, a proton in the core of a population 3 star might have waited millions of years before successfully completing this reaction. Yet with quintillions upon quintillions of protons attempting this reaction every second, enough succeeded to power the star. Once this first step created deuterium, a nucleus containing 1 proton and 1 neutron, the subsequent reactions proceeded much more quickly. The deuterium rapidly fused with another proton to form helium-3, releasing energy in the form of gamma rays. 2 helium-3 nuclei then collided and fused, producing helium-4 and releasing 2 protons back into the stellar core to participate in future reactions. The net result converted 4 hydrogen nuclei into 1 helium nucleus, with the missing mass transformed into energy, according to Einstein's famous equation. The energy released by each complete fusion cycle was tiny by everyday standards, about 4 times 10 to the negative 12th joules. But the sheer number of reactions occurring every second in a massive population 3 star's core was staggering. In a 100 solar mass star, something like 10 to the 38 reactions occurred each second, converting about 600 million tons of hydrogen into helium every second and releasing energy equivalent to billions of nuclear weapons. As population 3 stars aged and their cores became enriched with helium from hydrogen fusion, the conditions gradually changed. The core slowly contracted and heated as hydrogen was depleted, eventually reaching temperatures where helium itself could fuse. This transition marked a crucial turning point in the star's life and in the universe's chemical evolution. When core temperatures exceeded about 100 million Kelvin, helium nuclei began combining in a process called the triple alpha reaction. The triple alpha process was remarkable for its delicate precision. 3 helium-4 nuclei had to come together almost simultaneously to form carbon-12. The process actually occurred in 2 steps. First, 2 helium nuclei combined to form the unstable beryllium-8, which normally decayed back into 2 helium nuclei in about 10 to the negative 16 seconds. But occasionally, during that brief existence, a 3rd helium nucleus would collide with the beryllium-8, forming carbon-12 in an excited state. This excited carbon then released energy and settled into its ground state. The creation of carbon was a watershed moment in cosmic history. For the first time, the universe contained an element capable of forming complex chemistry, the backbone of organic molecules, and life as we know it. But in the extreme conditions of population 3 stellar cores, carbon was just another stepping stone to heavier elements. Some carbon nuclei captured additional helium nuclei to form oxygen-16, then neon-20, and so on. This alpha capture process created a ladder of elements, each 4 mass units heavier than the last. As the star's core continued to evolve, running out of helium and contracting further, temperatures rose to hundreds of millions of Kelvin. At these extreme temperatures, carbon itself began to fuse. Carbon fusion was a complex process with multiple possible pathways. 2 carbon-12 nuclei might combine to form magnesium-24, or they might produce neon-20 plus a helium nucleus, or sodium-23 plus a proton. Each pathway had different probabilities and energy releases, creating a rich mixture of fusion products. The pace of stellar evolution accelerated dramatically with each new fusion phase. While hydrogen fusion in a massive population 3R star might last 2 or 3 million years, helium fusion lasted only a few 100,000 years. Carbon fusion was completed in just a few thousand years. This acceleration occurred because heavier nuclei required higher temperatures to fuse, and at higher temperatures, reactions proceeded much faster. Additionally, energy losses through neutrino emission became increasingly important at high temperatures, requiring faster fusion rates to maintain the star's energy balance. Following carbon burning, the star entered a phase of neon fusion when core temperatures exceeded about 1.5 billion Kelvin. At these temperatures, high-energy gamma rays could break apart neon-20 nuclei, releasing helium nuclei that then fused with surviving neon to form magnesium and silicon. This photodisintegration process would become increasingly important in later fusion stages, creating a complex interplay between fusion building heavier elements and photodisintegration breaking them apart. Oxygen fusion began when temperatures reached about 2 billion Kelvin. Like carbon fusion, oxygen burning had multiple pathways, producing a variety of elements, including silicon, sulfur, argon, and calcium. The star's core was now generating elements that would one day form rocky planets. though still in tiny quantities compared to the hydrogen and helium that dominated the star's composition. The energy generation rate during oxygen fusion was enormous, but much of it was lost to neutrinos rather than contributing to the star's luminosity. Silicon fusion, beginning at temperatures above 3 billion Kelvin, was the final major fusion phase. But silicon fusion didn't proceed like earlier phases, where similar nuclei combined. Instead, it involved a complex network of reactions where silicon-28 and heavier nuclei partially photodisintegrated, releasing protons, neutrons, and helium nuclei that were then captured by other nuclei. This process gradually built up heavier and heavier elements, approaching iron 56, the most stable nucleus. The approach to iron was a death sentence for the star. Iron 56 sits at the peak of nuclear binding energy per nucleon. Fusion reactions producing elements lighter than iron release energy, as do fission reactions breaking apart elements heavier than iron. But creating elements heavier than iron through fusion absorbs energy rather than releasing it. When a star's core became dominated by iron, it had reached the end of the line for energy generation through fusion. Throughout these fusion phases, the star maintained a complex structure, like an onion with multiple layers. The iron core was surrounded by a shell of silicon fusion, then shells of oxygen, neon, carbon, helium, and finally hydrogen fusion. Each shell generated energy that helped support the outer layers against gravity. This multi-layered structure was highly unstable, with convection zones developing between some layers, mixing processed material and fresh fuel. The neutrino losses during advanced fusion stages deserve special attention. Neutrinos, ghostly particles that barely interact with matter, were produced copiously in the extreme conditions of late-stage stellar fusion. These neutrinos escape directly from the star's core, carrying away enormous amounts of energy. During silicon fusion, neutrino losses could exceed the star's photon luminosity by factors of thousands. This energy drain accelerated the star's evolution, forcing ever faster fusion rates to maintain equilibrium. Some population 3 stars might have been massive enough to experience exotic nuclear processes beyond standard fusion. At temperatures exceeding 5 billion Kelvin, electron-positron pairs could be created from high-energy gamma rays. Some of these positrons could be captured by protons, creating neutrons and neutrinos in a process called neutronization. This began converting the iron core into neutron-rich isotopes, presaging the complete neutronization that would occur during core collapse. The nuclear processes in population 3 stars also included S-process neutron capture during certain evolutionary phases. When fusion reactions produced free neutrons, these could be captured by heavy nuclei, building up neutron-rich isotopes. If the neutron flux was low enough, these isotopes had time to beta decay before capturing another neutron, gradually building heavier elements along the valley of beta stability. This slow neutron capture process could create elements heavier than iron even before the star's death, though in relatively small quantities. The energy generation patterns in population 3 stars showed remarkable variability. During stable fusion phases, energy generation was smooth and centrally concentrated. But during transitions between fusion phases, the star might experience thermal pulses, brief periods of explosive fusion that could temporarily increase luminosity by factors of hundreds or thousands. These pulses could drive convection that dredged processed material to the surface, potentially enriching the star's envelope with heavy elements. The balance between energy generation and loss was precarious throughout a population 3 star's life. Any disruption to this balance could trigger dramatic responses. If fusion rates dropped slightly, the core would contract and heat up, increasing fusion rates. If fusion rates increased too much, the core would expand and cool, reducing fusion rates. This feedback mechanism maintained stability during most of the star's life, but became increasingly unstable as the star approached its death. Understanding these nuclear processes requires sophisticated modelling that accounts for thousands of different nuclear reactions, each with temperature-dependent rates. The nuclear physics involved pushes our knowledge to its limits, requiring extrapolation of measured reaction rates to extreme conditions never achieved in laboratories. Uncertainties in key reaction rates can significantly affect predictions of stellar evolution and nucleosynthesis. The nuclear legacy of population the 3 stars extended far beyond their own lives. Every element they created through fusion would be expelled into space during their deaths, enriching the primordial gas and enabling the formation of second-generation stars with different properties. The specific mixture of elements produced depended on the star's mass and evolutionary history, creating a chemical fingerprint that astronomers still search for today in the oldest surviving stars. The death of a population 3 star was not a gentle fading, but a violent catastrophe that lit up the early universe and forever changed its chemical composition. These first stellar deaths were among the most energetic events in cosmic history, and their effects rippled across space and time, influencing galaxy formation, star formation, and ultimately the existence of planets and life itself. When a massive population 30 star exhausted its nuclear fuel, the delicate balance that had maintained it for millions of years finally failed. The iron core, that stellar graveyard where fusion could generate no more energy, grew through shell burning until it approached a critical mass called the Chandrasekhar limit, about 1.4 times the mass of our Sun. At this point, the core was supported primarily by electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed too close together. But this support had its limits. As the iron core grew beyond the Chandrasekhar mass, electron degeneracy pressure could no longer support it against gravity. The collapse that followed was catastrophically swift. In less than a second, the core compressed from roughly the size of Earth to a sphere just a few dozen kilometers across. The density increased by factors of billions, reaching nuclear densities where matter itself began to break down. Protons and electrons were crushed together to form neutrons, releasing a flood of neutrinos that carried away enormous amounts of energy. The core collapse proceeded at velocities approaching a quarter of the speed of light. As the outer layers of the core fell inward, they eventually encountered nuclear density, where the strong nuclear force suddenly provided enormous resistance to further compression. The core bounced, sending a powerful shockwave racing outward through the star. This shockwave, carrying about 10 to the 51 ergs of energy, would ultimately tear the star apart, though its journey was far from simple. Initially, the shockwave stalled as it encountered the massive overlying layers still falling inward. The shock lost energy, breaking apart iron nuclei through photodisintegration, temporarily halting its outward progress. For a few hundred milliseconds, the fate of the explosion hung in the balance. In many modern supernovae, neutrino heating behind the shock provides the extra push needed to revive it. But in population of 3 stars, with their massive envelopes and potentially different core structures, the explosion mechanism might have been even more complex. The revival of the shock and its eventual breakout from the star's surface depended critically on the star's mass and structure. For population the 3 stars between about 10 and 40 solar masses, the explosion probably resembled modern core collapse supernova, though potentially more energetic due to the star's compact structures and massive envelopes. The explosion energy could exceed 10 to the 52 ergs, 10 times more powerful than typical supernovae today. But for more massive population 3 stars, between about 140 and 260 solar masses, a completely different death awaited. These stars experienced pair instability supernovae, a mechanism that doesn't occur in the modern universe because no stars today reach such masses. In these stars, the core became so hot that gamma rays spontaneously created electron-positron pairs. This pair production reduced the radiation pressure supporting the star, triggering a catastrophic collapse. Unlike core collapse supernovae, pair instability explosions didn't leave behind any remnant. The collapse triggered explosive oxygen and silicon fusion throughout the star, releasing enough energy to completely unbind it. The explosion energy could exceed 10 to the 53 ergs, making these among the most powerful explosions in the universe's history. The entire star, all 100 or 200 solar masses of it, was blown apart and dispersed into space. For the most massive population 3 stars, those exceeding about 260 solar masses, even pair instability couldn't destroy them. These monsters collapsed directly to black holes, their gravity so strong that not even a supernova explosion could escape. Some material near the surface might have been expelled, but most of the star vanished behind an event horizon, creating black holes of 100 solar masses or more. These direct collapse black holes might have been the seeds for the supermassive black holes we see in galaxy centers today. The chemical yields from population 3 at supernovae were extraordinary. A single pair instability supernova could produce more than 50 solar masses of iron, along with comparable amounts of oxygen, silicon, and other elements. The explosion synthesized elements throughout the periodic table, creating the first calcium, titanium, chromium, manganese, cobalt, nickel, copper, and zinc in the universe. These freshly minted elements were ejected at velocities of thousands of kilometers per second, enriching the surrounding gas. The distribution of elements from population 3 supernova differed markedly from modern supernova. Without the moderating effects of stellar winds removing the outer envelope, population 3 explosions processed a larger fraction of the star's mass. The yields were also affected by the star's unique structure and evolution. Some models predict unusual abundance patterns, with odd-even effects where elements with even numbers of protons were significantly more abundant than their odd-numbered neighbours. The explosion itself was a spectacular light show that would have been visible across the observable universe. The optical display began when the shock wave burst through the star's surface, heating it to hundreds of thousands of Kelvin. For pair instability supernova, the peak luminosity could exceed 10 to the 44 ergs per second, billions of times brighter than our Sun, and visible from billions of light years away. The light curve, how brightness changed with time, stretched over many months as radioactive nickel-56 decayed to cobalt-56 and then iron-56, powering the extended glow. The immediate environment around an exploding population 3 star was transformed instantly. The explosion drove a blast wave into the surrounding gas, heating it to millions of Kelvin and accelerating it to thousands of kilometers per second. This hot, shocked gas glowed in X-rays and ultraviolet light, creating an expanding bubble that could eventually reach sizes of hundreds of light years. The blast wave swept up and compressed surrounding gas, potentially triggering the formation of second-generation stars enriched with heavy elements. The energy injection from population 3 supernovae had profound effects on their host dark matter halos. For the smallest halos, those around 1 million solar masses, a single supernova could completely unbind the gas, blowing it out of the halo's gravitational well. This feedback effectively sterilized small halos, preventing further star formation for hundreds of millions of years until the gas could cool and fall back in. Larger halos might retain some gas, but star formation would still be suppressed for extended periods. The heavy elements ejected by population 3 supernovae didn't spread uniformly through space. Instead, they travelled in clumps and filaments, creating a highly inhomogeneous distribution of metals in the early universe. Some regions became enriched to nearly solar abundances, while others remained pristine. This patchy metal distribution influenced where and how second-generation stars formed, creating a complex pattern of chemical evolution that astronomers still trace today. Beyond heavy elements, population 3 supernovae might have produced more exotic particles. The extreme conditions during explosion could have created hypothetical particles, like axions or sterile neutrinos, potential dark matter candidates. The explosions also generated cosmic rays, high-energy particles that travelled at near light speed through the early universe. These cosmic rays could have provided additional heating and ionization, affecting the thermal and chemical state of primordial gas across vast distances. The gravitational waves produced by asymmetric population 3 supernova rippled through space-time itself. While too high frequency for current detectors, these ancient gravitational waves contributed to a stochastic background that might be detectable by future space-based observatories. The strength and frequency distribution of these waves encode information about the masses and explosion mechanisms of the first stars. Some population 3 stars might have experienced multiple eruptions before their final explosion. Pulsational pair instability could have caused massive stars to undergo several partial explosions, each ejecting part of the envelope while leaving the core intact. These eruptions would have pre-enriched the surrounding medium with heavy elements, creating shells of processed material that the final explosion would later encounter and shock. The black holes left behind by some population 3 deaths became important players in the early universe. These intermediate mass black holes, ranging from tens to hundreds of solar masses, could have grown through accretion and mergers to become the seeds of supermassive black holes. When two such black holes merged, they produced gravitational waves that might be detectable by current and future observatories, providing a direct window into population 3 star formation. The cooling and fragmentation of supernova-enriched gas led to fundamentally different star formation. Once gas contained even trace amounts of heavy elements, perhaps 1/10,000th of solar abundance, it could cool much more efficiently through metal line radiation. This enhanced cooling allowed smaller gas masses to collapse, producing less massive stars more similar to those forming today. The transition from population 3 to population 2 star formation was gradual and patchy, occurring at different times in different regions. The supernova remnants from population 3 explosions evolved differently from modern remnants. The lack of a pre-existing circumstellar medium meant the blast wave expanded into relatively pristine gas. The remnants could remain hot and luminous for millions of years, continuing to inject energy into their surroundings long after the initial explosion. These long-lived remnants served as beacons marking the sites where the universe's chemical enrichment began. Some population 3 supernovae might have triggered a chain reaction of star formation. As their blast waves compressed surrounding gas clouds, they could have induced gravitational collapse in regions that were marginally stable. These triggered stars would form from gas already enriched by the supernova, creating a second generation with dramatically different properties. This process of a self-propagating star formation might have rapidly transformed entire regions from primordial to metal-enriched. The deaths of population 3 stars also marked the end of an era. Once a region had been enriched by even a single supernova, it could never return to its primordial state. The universe had crossed a one-way threshold from chemical simplicity to complexity. Every subsequent generation of stars would form from gas bearing the chemical fingerprints of these first stellar deaths, layers upon layers of nucleosynthesis building the periodic table we know today. The explosions of population 3 stars didn't just mark endings, they were beginnings of a new chapter in cosmic history. The heavy elements forged in their cores and explosions spread through space like seeds, fundamentally transforming the universe's capacity for complexity. Let's explore how these first metals changed everything, enabling the formation of new types of stars, planets, and ultimately life itself. When a population 3 supernova exploded, its newly created elements didn't spread uniformly through space. The explosion drove metals outward in a complex pattern of shells, filaments, and clumps. The heaviest elements, those produced in the explosion itself, were concentrated in dense knots moving at thousands of kilometers per second. Lighter elements from the star's outer layers spread more uniformly, creating gradients of composition that would influence future star formation for millions of years. The mixing of these metals with primordial gas was a slow and complicated process. Initially, the hot supernova ejecta and the cold surrounding gas remained largely separate, like oil and water. The interface between them was marked by instabilities, where fingers of hot metal-rich gas penetrated into the cold primordial medium, while bubbles of pristine gas rose through the enriched material. This Rayleigh-Taylor instability, similar to what happens when you pour cream into coffee, gradually increased the surface area between the two fluids, promoting mixing. Turbulence played a crucial role in distributing metals through the early universe. As blast waves from supernova encountered density variations in the surrounding gas, they generated vortices and eddies at all scales. These turbulent motions stirred the metals through increasingly large volumes, though the mixing was far from perfect. Even today, 13 billion years later, we can observe stars with unusual abundance patterns that reflect incomplete mixing in their natal gas clouds. The cooling properties of metal-enriched gas differed dramatically from primordial material. Even tiny amounts of carbon and oxygen, perhaps just 1/10,000th of their abundance in our Sun, provided new pathways for gas to radiate away heat. Carbon atoms could be excited by collisions and emit photons in the far infrared, while oxygen provided additional cooling lines. This enhanced cooling meant that smaller gas masses could overcome thermal pressure and collapse under gravity, enabling the formation of less massive stars. The first population 2 stars, formed from gas enriched by population 3 supernova, were revolutionary in their ordinariness. With masses ranging from a fraction of our Sun's mass to perhaps 50 solar masses, they resembled stars forming in our galaxy today, far more than their massive population 3 predecessors. These second-generation stars could live much longer than population 3 stars, with the smallest potentially surviving for trillions of years, far longer than the current age of the universe. The abundance patterns in early population 2 stars provide forensic evidence about their population 3 progenitors. Some ancient stars show enhancement in alpha elements like oxygen, magnesium, and silicon relative to iron, suggesting enrichment by massive core collapse supernova. Others display unusual ratios of odd to even elements, potentially indicating pair instability supernova enrichment. These chemical fingerprints allow astronomers to work backward, inferring the properties of long-dead population 3 stars from their surviving descendants. Carbon-enhanced metal-poor stars represent a particularly interesting category of early population 2 stars. These objects show strong carbon enhancement relative to iron, sometimes by factors of 100 or more. One explanation is that they formed from gas enriched by relatively low-mass population 3 stars that experienced significant carbon dredge-up before exploding. Alternatively, they might have acquired carbon from a binary companion. These carbon-enhanced stars provide crucial constraints on the mass distribution of population 3 stars. The spatial distribution of metals in the early universe was highly inhomogeneous. Some regions became enriched to nearly solar metallicity by multiple supernovae, while others remained nearly pristine for hundreds of millions of years. This patchy distribution created diverse environments for star formation, with metal-rich pockets hosting population 2 star clusters, while nearby pristine regions might still form massive population 3 stars. This coexistence of stellar populations with vastly different properties must have created spectacular contrasts in the early universe. The formation of star clusters changed fundamentally with metal enrichment. While population 3 stars probably formed in isolation or small groups, metal-enriched gas could fragment into hundreds or thousands of stars simultaneously. The first globular clusters, dense spheres containing hundreds of thousands of stars, began forming from gas enriched by population 30 supernovae. These ancient clusters, some of which survive today, preserve chemical evidence of the early universe's rapid enrichment. Metals also enabled new feedback mechanisms that regulated star formation. Radiation from young stars could heat dust grains, which then warmed the surrounding gas through collisions. Stellar winds, driven by radiation pressure on metal atoms in stellar atmospheres, became more powerful with increasing metallicity. These feedback processes prevented gas from collapsing too efficiently, establishing a more sustainable rate of star formation that could continue for billions of years. The role of metals in planet formation cannot be overstated. Rocky planets like Earth require elements heavier than hydrogen and helium, elements that didn't exist before population 3 stars created them. The first planets probably formed around population 2 stars from disks enriched with supernova products. These early planets would have had unusual compositions, perhaps enhanced in certain elements, depending on which type of supernova enriched their parent gas cloud. The chemical evolution of galaxies began with population 3 enrichment, as metals spread through dark matter halos, and between them they established gradients and patterns that would persist for billions of years. The centers of halos, where star formation was most intense, became more metal-rich than the outskirts. Galactic winds driven by supernovae could transport metals far beyond their birth sites, enriching the intergalactic medium and seeding future galaxy formation. Some population 2 stars formed in extreme environments, shaped by population 3 deaths. Near recent supernova sites, gas was hot, turbulent, and highly enriched. These conditions might have produced unusual stars, perhaps with rapid rotation or strong magnetic fields inherited from their chaotic birthplaces. Other population 2 stars formed in the quiet outskirts of halos, from gas that had been gently enriched by metals spreading slowly from distant explosions. The transition from population 3 to population 2 wasn't sharp, but occurred gradually over cosmic time. Mathematical models suggest that by about 500 million years after the Big Bang, most star formation was population 2, though isolated population 3 stars might have continued forming in pristine pockets for another few hundred million years. This extended transition period created a rich diversity of stellar populations in the early universe. Binary star evolution added complexity to chemical enrichment patterns. When one star in a population 2 binary exploded as a supernova, it could contaminate its companion with processed material. If the companion later exploded, it would release a mixture of elements from both stars, creating unusual abundance patterns. Mass transfer between binary components could also alter their evolution, producing supernovae with non-standard yields that further enriched the chemical diversity of the early universe. The formation of molecules became increasingly important as metallicity rose. Carbon monoxide, water, and other molecules could form in metal-enriched gas, providing additional cooling and enabling the formation of even lower-mass stars. These molecules also traced gas dynamics, allowing astronomers studying the early universe to map gas flows and identify sites of active star formation. The molecular universe that emerged from population 3 enrichment was far more complex than the simple atomic gas that preceded it. Dust grains, tiny solid particles of carbon, silicon, and other heavy elements began forming in the ejecta of supernovae and the atmospheres of evolved stars. These grains, though initially rare, would eventually become crucial for star and planet formation. Dust provided surfaces for molecular formation, shielded gas from destructive radiation, and enabled more efficient cooling. The appearance of dust marked another irreversible step in cosmic evolution, adding a solid component to what had been a purely gaseous universe. The metals produced by population 3 stars also affected the universe's thermal evolution. Metal-line cooling changed how gas responded to heating from stars and active galactic nuclei. This altered the balance between hot and cold gas phases, affecting everything from galaxy formation to the growth of supermassive black holes. The universe's metabolism, the rate at which it processed gas into stars, was fundamentally changed by the chemical complexity introduced by population 3 deaths. Radioactive isotopes from population 3 supernovae provided unique traces of early chemical evolution. Aluminum-26, with its half-life of 700,000 years, could have heated and melted the first solid particles in the universe. Nickel-56, decaying to cobalt-56 and then iron-56, powered the optical display of supernovae for months after explosion. These radioactive decays not only provided energy, but also created gamma rays that could trigger additional nuclear reactions, further modifying the chemical composition of supernova ejecta. The enrichment process created fascinating chemical anomalies that astronomers still puzzle over today. Some ancient stars show enormous overabundances of certain elements, while being deficient in others. These peculiar patterns might reflect contamination by a single nearby supernova, rather than well-mixed enrichment from multiple sources. Each anomalous star is like a message in a bottle from the early universe, preserving information about individual population 3 explosions that occurred over 13 billion years ago. As second-generation stars lived and died, they added their own contributions to the universe's growing chemical complexity. Population 2 supernovae had different yields than their population 3 predecessors, producing more iron peak elements relative to alpha elements. This began establishing the chemical trends we observe in galaxies today, where stellar populations of different ages show distinct abundance patterns. The universe was developing a chemical chronology, with element ratios serving as clocks dating when particular regions were enriched. The spread of metals beyond individual dark matter halos into the intergalactic medium was a crucial development. Galactic winds, driven by the collective effect of many supernovae, could accelerate enriched gas to velocities exceeding the escape speed of their host halos. This metal-enriched gas spread through the cosmic web, contaminating pristine gas flows and ensuring that even isolated regions couldn't remain metal-free indefinitely. The universe was becoming chemically connected on ever larger scales. Some regions experienced runaway enrichment, where the formation and death of massive stars created a positive feedback loop. Metals from the first supernova enabled more efficient cooling and star formation, leading to more supernova, more metals, and even more star formation. These starbursts could enrich gas to near-solar metallicity in just a few 100 million years, creating pockets of chemical maturity in an otherwise young universe. These enriched regions might have hosted the first Earth-like planets, though still billions of years before life could emerge. The chemical stratification within early galaxies reflected their formation history. Gas that fell in early, when metallicity was low, formed stars in the galactic halo with distinct chemical signatures. Later, infalling gas, pre-enriched by population 3 explosions elsewhere, formed different stellar populations. This created an archaeological record within galaxies, with stellar chemistry revealing the sequence and timing of galactic assembly. Modern observations of ancient stars in our own galaxy's halo still read this record today. The quest to observe population 3 stars directly represents one of astronomy's greatest challenges and most tantalizing goals. Though these first stars vanished billions of years ago, their influence echoes through cosmic history in ways we can measure today. Let's explore the detective work astronomers undertake to uncover evidence of these ancient giants and the revolutionary observatories that might finally catch them in the act of shining. The most direct approach to finding population 3 stars involves looking back in time by observing the most distant reaches of the universe. Light from the edge of the observable universe has travelled for over 13 billion years to reach us, showing us the universe as it was when population 3 stars were actively forming and dying. But the enormous distances involved make individual population 3 stars impossible to resolve with current technology. Even the massive James Webb Space Telescope, humanity's most powerful infrared observatory, cannot directly image individual stars at such cosmic distances. Instead, astronomers search for the collective signature of population 3 star formation in early galaxies. These first stellar populations would have produced distinctive spectral features, particularly strong helium emission lines and an absence of metal absorption lines. The intense ultraviolet radiation from massive population 3 stars would have ionized helium in surrounding gas, creating characteristic emission when electrons recombined with helium ions. This helium-2 emission at 1640 angstroms, redshifted into the infrared by cosmic expansion, provides a potential smoking gun for population 3 activity. The James Webb Space Telescope has revolutionized our ability to study the early universe since its launch. Its unprecedented infrared sensitivity allows it to peer through the cosmic fog to epochs when the universe was just a few 100 million years old. While JWST hasn't definitively detected population 3 stars yet, it has revealed surprisingly mature galaxies at very early times, suggesting that star formation, including potentially population 3 star formation, began earlier than previously thought. One of the most promising signatures of population 3 stars comes from their spectacular deaths. Pair instability supernovae from very massive population 3 stars would have been visible across the observable universe, appearing as ultraluminous transients lasting many months. These explosions would have distinctive light curves, powered by the decay of enormous quantities of radioactive nickel-56. Modern surveys like the Legacy Survey of Space and Time at the Vera Rubin Observatory are designed to detect such rare transients, potentially catching population 3 explosions in real time. The chemical abundance patterns in extremely metal-poor stars in our own galaxy provide fossilized evidence of population 3 nucleosynthesis. These ancient stars, formed from gas enriched by perhaps just 1 or 2 population 3 supernovae, preserve chemical fingerprints of their progenitors. The Sloan Digital Sky Survey and other projects have identified hundreds of stars with less than 1,000th of solar metallicity, and a handful with less than 1/10,000th. The most metal-poor star known has less than 1/10,000,000th of the Sun's iron abundance, possibly reflecting enrichment by a single population 3 supernova. Each ultra-metal-poor star tells a unique story about population 3 enrichment. Some show strong enhancement in carbon relative to iron, suggesting formation from gas enriched by relatively low-mass population 3 stars. Others display unusual patterns of neutron capture elements, potentially indicating enrichment by exotic processes like magneto-rotationally driven supernova. By studying large samples of these ancient stars, astronomers can statistically reconstruct the mass distribution and explosion properties of population 3 stars. Gravitational waves offer an entirely different window into population 3 stars. When two massive population 3I stars in a binary system died and left behind black holes, those black holes could eventually merge, producing gravitational waves. The LIGO and Virgo observatories have already detected numerous black hole mergers, and some involve black holes massive enough to potentially be population 3 remnants. The proposed space-based Lesser Observatory will be sensitive to mergers at much higher redshifts, potentially detecting population 3 black hole mergers directly. The cosmic infrared background, a diffuse glow of infrared light from all sources throughout cosmic history, contains accumulated radiation from population 3 stars. Careful analysis of fluctuations in this background might reveal the clustering pattern of the first stars. The Spitzer Space Telescope and other infrared observatories have detected excess fluctuations that some researchers attribute to population 3 stars, though alternative explanations involving early black holes remain viable. 21 centimeter radiation from neutral hydrogen provides another probe of the population 3 era. The first stars would have heated and ionized hydrogen in their vicinity, creating bubbles that would appear as dark spots in 21 centimeter maps of the early universe. Radio observatories like the Square Kilometre Array, currently under construction, will map these ionization bubbles, potentially revealing the distribution and properties of population 3 stars. The heating patterns around the first stars would be distinctive, as their hard ultraviolet spectra penetrated farther into the neutral medium than radiation from metal-enriched stars. High redshift gamma-ray bursts might originate from the deaths of rapidly rotating population 3 stars. These explosions, among the most energetic events in the universe, can be detected from enormous distances. The Swift satellite and other gamma-ray observatories have detected bursts from when the universe was less than 1 billion years old. Some of these might be population 3D explosions, though proving this requires detailed spectroscopic follow-up to confirm the absence of metals. The reionization of the universe, when radiation from the first stars and galaxies ionize the neutral hydrogen-filling space, carries information about population 3 stars. The timing, duration, and patchiness of reionization depend on the properties of the ionizing sources. Observations of the cosmic microwave background by the Planck satellite suggest reionization occurred relatively late, implying that population 3 stars alone couldn't have reionized the universe. This constraint helps limit models of population 3 star formation and their contribution to early cosmic history. Numerical simulations play a crucial role in the search for population 3 stars by predicting what we should observe. Sophisticated computer models follow the collapse of primordial gas clouds, the formation of the first stars, their feedback on surrounding gas, and their eventual explosions. These simulations make specific predictions for observable signatures, from the colours of population 3 star clusters to the chemical yields of their supernova. As computational power increases Simulations can include more physical processes and achieve higher resolution, making increasingly precise predictions. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct massive surveys for transient events, potentially detecting hundreds of population 3 supernovae. Its wide field of view and infrared sensitivity make it ideal for finding rare explosive events in the early universe. Combined with rapid follow-up spectroscopy from ground-based telescopes, Roman could definitively identify population 3 explosions through their lack of metal absorption lines. Future 30-meter class ground-based telescopes like the Extremely Large Telescope, Giant Magellan Telescope, and 30-meter telescope will provide unprecedented resolution and sensitivity for studying the early universe. These observatories could potentially resolve individual star-forming regions in galaxies at redshifts of 10 or higher, distinguishing between population 3 and population 2 star formation through spectroscopic signatures. They might even detect individual supergiant population 3 stars in gravitationally lensed galaxies. The search for population 3 stars has revealed surprises about the early universe. Observations suggest that metal enrichment proceeded faster than simple models predicted, with some galaxies showing near-solar metallicities when the universe was less than 1 billion years old. This rapid enrichment implies either that population 3 stars formed very efficiently early on, or that population 2 stars contributed more to early enrichment than expected. The full story likely involves complex feedback processes we're still working to understand. Astroarchaeology, the study of ancient stellar populations to reconstruct cosmic history, has emerged as a powerful tool for understanding population Thra stars. By combining observations of metal-poor stars in our galaxy with those in nearby dwarf galaxies and the halos of other galaxies, astronomers can build a comprehensive picture of early chemical evolution. Each old star is a time capsule, preserving information about conditions when the universe was young. The philosophical implications of the search for population 3 stars extend beyond astronomy. These first stars represent the universe's first step toward complexity, the beginning of the cosmic journey that would eventually lead to planets, life, and consciousness. Finding direct evidence of population 3 stars would complete our understanding of cosmic evolution, linking the Big Bang to the rich universe we inhabit today. Every observation brings us closer to witnessing the universe's first lights, those ancient giants that began the transformation of cosmic darkness into the star-filled cosmos we know. As we stand on the threshold of revolutionary discoveries about the universe's first stars, the coming decades promise to transform our understanding of these cosmic pioneers. New technologies, innovative observational strategies, and deeper theoretical insights are converging to finally lift the veil on population 3 stars. Let's explore what the future might reveal about these ancient giants and contemplate their profound significance for our cosmic story. The next generation of space telescopes will peer deeper into space and time than ever before. Beyond the James Webb Space Telescope, concepts for even more powerful observatories are taking shape. The proposed Habitable Worlds Observatory, though primarily designed to study exoplanets, would have the sensitivity to detect the integrated light from population 3 star clusters in the early universe. Its advanced coronagraph could block the glare from foreground galaxies, revealing faint population 3 regions that current telescopes cannot detect. Far infrared observatories operating at wavelengths beyond JWST's range could detect the red-shifted light from population 3 stars at even earlier cosmic epochs. The proposed Origin Space Telescope would have unprecedented sensitivity to the specific wavelengths where population 3 signatures are strongest. It could map the transition from population 3 to population 2 star formation across cosmic time, revealing how metal enrichment propagated through the early universe. The concept of a lunar farside radio observatory has gained renewed interest as we prepare to return to the Moon. Shielded from Earth's radio interference by the Moon itself, such an observatory could detect the faint 21-centimetre signals from the cosmic dark age and the era of first stars. These observations would reveal the heating and ionization patterns around population 3 stars, providing information about their masses, lifetimes, and spatial distribution that no other technique can access. Gravitational wave astronomy is entering a golden age that will revolutionize our understanding of population 3 stars. As LIGO and Virgo continue upgrading their sensitivity, they'll detect black hole mergers from increasingly early cosmic epochs. The proposed Einstein telescope and Cosmic Explorer, with sensitivity 10 times better than current detectors, could observe population 3 black hole mergers throughout the observable universe. These observations would directly measure the mass distribution of population 3 remnants. The space-based gravitational wave observatory LISA, launching in the 2030s, will detect lower frequency gravitational waves from more massive black hole mergers. If intermediate mass black holes from population 3 stars grew into supermassive black holes, LISA will witness key stages of this growth. The gravitational wave signatures encode information about the black hole's formation history, potentially revealing whether they originated from population 3 stars. Advances in computer simulation are equally important for understanding population 3 stars. Exascale supercomputers, capable of a quintillion calculations per second, can now simulate population 3 star formation with unprecedented realism. These simulations include magnetic fields, radiation transport, chemical networks, and other physical processes previously too complex to model accurately. As computational power continues growing, we'll be able to simulate entire populations of population 3 stars and their effects on early galaxy formation. Machine learning and artificial intelligence are transforming how we search for population 3 signatures in astronomical data. Neural networks trained on simulated spectra can identify subtle population 3 features in noisy observations that human analysts might miss. AI can also help us understand the complex relationships between observable properties and underlying physical processes, extracting maximum information from limited data. The discovery of gravitationally lensed population 3 regions could provide the breakthrough we've been seeking. Strong gravitational lensing by foreground galaxy clusters can magnify distant sources by factors of hundreds or thousands, potentially making individual population 3 star-forming regions visible. The Hubble Frontier Fields program and similar JWST observations have already revealed lensed galaxies from when the universe was just a few 100 million years old. With careful searching, we might find a lensed population 3 region bright enough for detailed spectroscopic study. Laboratory astrophysics is providing crucial data for interpreting population 3 observations. Experiments at facilities like the National Ignition Facility can recreate the extreme conditions inside population 3 stars, measuring nuclear reaction rates and opacity data that feed into stellar models. These measurements reduce uncertainties in our theoretical predictions, making it easier to recognize population 3 signatures when we see them. The interdisciplinary connections between population 3 research and other fields continue to deepen. Particle physicists studying dark matter are interested in population 3 stars as potential dark matter laboratories. The extreme conditions in these stars might have produced exotic particles or revealed new physics beyond the standard model. Cosmologists use population 3 constraints to test models of early universe physics, including inflation and baryogenesis. The astrobiological implications of population 3 stars extend far into the future. By creating the first heavy elements, these stars set in motion the chemical evolution that would eventually enable life. Understanding population 3 stars helps us estimate when in cosmic history the conditions for life first became possible. This knowledge informs our search for life elsewhere in the universe and our understanding of our own cosmic origins. Cultural and philosophical perspectives on population 3 stars continue evolving as our scientific understanding deepens. These first stars represent the universe's first creative act, transforming simple hydrogen and helium into the rich periodic table that makes our existence possible. They remind us that we are connected to the cosmos in the most fundamental way. Our very atoms forged in stellar furnaces billions of years ago. Educational initiatives are bringing population 3 science to broader audiences. Planetarium shows, virtual reality experiences, and interactive simulations allow people to witness the birth and death of the first stars. These tools make the abstract concrete, helping students and the public understand their cosmic heritage. As we discover more about population 3 stars, these educational resources will evolve, sharing the excitement of discovery with the world. International collaboration remains essential for population 3 research. No single country can build and operate all the necessary observatories. The Square Kilometre Array involves over a dozen nations. LISA is a European Space Agency mission with NASA participation, and the Extremely Large Telescope is funded by a consortium of European countries. This global cooperation reflects the universal nature of our quest to understand the first stars. The timeline for major population 3 discoveries looks promising. Within the next 5 years, JWST deep fields might reveal statistical evidence for population 3 star formation. The 2030s could bring direct detection of population 3 supernovae with Roman and the first population 3 black hole mergers with LISA. By the 2040s, with 30-metre telescopes fully operational and next-generation space observatories deployed, we might have detailed observations of individual population 3 star-forming regions. Yet mysteries will undoubtedly remain. Even as we answer current questions about population 3 stars, new puzzles will emerge. We might discover that population 3 stars were more diverse than expected, with different formation modes in different environments. Or we might find that the transition from population 3 to population 2 was more complex than our models suggest, involving intermediate populations with properties we haven't anticipated. The search for population 3 stars teaches us patience and persistence. These stars existed for only a brief moment in cosmic history, a few 100 million years out of nearly 14 billion. Finding evidence of their existence requires looking across billions of light years with instruments of extraordinary sensitivity. Yet the effort is worthwhile, for these stars hold keys to understanding our cosmic origins. As we near the end of our gentle journey through the story of population 3 stars, take a moment to appreciate the profound connection between those ancient giants and ourselves. Every carbon atom in your body, every oxygen atom you breathe, every iron atom in your blood was created either in a star or in its explosive death. While these specific atoms probably came from more recent stellar generations, the process began with population 3 stars. They were the universe's first alchemists, transforming primordial hydrogen into the elements of life. The legacy of population 3 stars extends beyond their chemical contributions. They began the process of cosmic reionization, clearing away the neutral hydrogen fog that filled the early universe. They provided the first sources of heat and turbulence that shaped galaxy formation. They created the first black holes that would grow into the monsters we see in galaxy centers today. In every aspect of cosmic evolution, we see the influence of these first stars. Looking up at the night sky, we see stars of many types and ages, but none are population 3 stars. They are all gone, extinct like cosmic dinosaurs, leaving only indirect evidence of their existence. Yet in another sense, they are all around us. Their ashes are incorporated into every subsequent generation of stars, planets, and life. We are built from their remnants, living monuments to their ancient glory. The story of population the 3 stars is ultimately a story about beginnings and endings, simplicity and complexity, darkness and light. It's a story that connects the largest scales of the universe to the smallest, linking cosmology to chemistry to biology. It reminds us that the universe has a history, that it has evolved and changed, and that we are part of that continuing evolution. As you drift off to sleep tonight, perhaps you'll dream of those first stars igniting in the cosmic darkness. Picture them scattered across the young universe like the first flowers of spring, each one a beacon of light and a factory of new elements. See their violent deaths spreading seeds of complexity through space, enriching pristine gas clouds and enabling new generations of stars. Watch as the universe transforms from simple to complex, from dark to light, from lifeless to living. The search for population 3 stars continues, driven by humanity's deep desire to understand our origins. Each new observation, each theoretical insight, each technological advance brings us closer to seeing these cosmic firstborn. When we finally detect them directly, whether through their explosions, their gravitational waves, or their collective light, it will mark a milestone in human understanding comparable to discovering our evolutionary origins or decoding DNA. But even without direct detection, we know population 3 stars existed. The evidence is written in the chemistry of ancient stars, in the masses of black holes, in the very existence of elements heavier than lithium. These cosmic pioneers may be gone, but their legacy endures in every atom of carbon, every molecule of water, every grain of dust in the universe. So as you settle into sleep, remember that you carry within you the legacy of the universe's first stars. You are made of cosmic history, your atoms witnesses to stellar birth and death across billions of years. The story of population the 3 stars is your story, written in the very substance of your being. Sleep well, my fellow travellers, knowing that you are connected to the cosmos in the most profound and beautiful way. Sweet dreams, and thank you for joining me on this gentle journey through the story of the universe's first lights. If you enjoyed exploring the cosmic dawn with me, please consider subscribing to follow along on future adventures through space and time. Until next time, this is Sleepy Parallax, wishing you peaceful slumbers filled with stellar dreams.